In this lesson, we will learn something of the differences between direct current and alternating current. This presentation does not cover all we need to know on the topic. Additional information can be found in the General Aviation Maintenance Technician's Handbook and in the Acceptable Methods, Techniques, and Practices of Aircraft Inspection and Repair. We have already learned that batteries produce direct current, and by direct current we mean that the voltage and current are constant and current always flows from the negative terminal to the positive terminal. The electricity from our wall socket, however, is alternating current, where the voltage and current go from zero to a peak value cyclically, and the current changes direction each half of a cycle, and the voltage changes polarity each half of a cycle. To summarize the differences between direct current and alternating current, direct current flows in one direction. Alternating current, however, flows first in one direction and then in the opposite direction. Direct current voltage has a fixed polarity. Alternating current voltage, however, switches polarity back and forth. A direct current power grid, as proposed early on by Thomas Edison, would have required a power station about every 2 miles because of the difficulty in transmitting direct current power over long distances. The alternating current power grid advocated by Tesla allows the transmission of electrical power over much longer distances by use of transformers. A series of transformers allows the power companies to step down the voltage until it arrives at our house at about 120 volts. Most of our smaller aircraft operate on direct current only systems. Many larger aircraft, however, incorporate alternating current power into their electrical systems. Larger aircraft can require many miles of electrical wiring. The A380, for example, requires 2,000 miles of electrical wiring. Because through the use of transformers, alternating current power can be transferred over smaller gauge wires than can direct current power, saving weight and the expense and space required of heavier gauge wiring. Also, the equipment required to generate alternating current is smaller, lighter, and less likely to cause radio interference than those used to create direct current. The electrical power generated by our hydroelectric, nuclear, coal, and natural gas-powered power plants, as well as that produced by the alternators in our vehicles and aircraft, is all generated by rotating a conducting coil through the lines of flux within a magnetic field. As the current or voltage increases from zero to a peak value and then back to zero, and as it changes direction and polarity, their values at any moment can be plotted on a sine wave. The faster a conducting wire cuts through lines of magnetic flux, the greater the voltage and current being generated. The conducting wire cuts through the lines of magnetic flux fastest when moving perpendicular to the lines of flux, and does not cut through them at all when moving parallel to the lines of flux. This series of pictures shows that voltage and current reach their peak when moving 90 degrees to the lines of flux, and go to zero when moving 0 degrees to the lines of flux. This series of pictures also illustrate why polarity and current direction change each 180 degrees rotation of the conducting wire. In the sinusoidal alternating current waveform, the vertical axis represents the amplitude of the alternating current or voltage, and the horizontal line represents the angle at which the conducting wire is cutting through the lines of magnetic flux. Peak voltage is the voltage measured from the baseline of an alternating current waveform to its maximum or peak value. Peak-to-peak voltage is the voltage measured from the maximum positive level to the maximum negative level. Alternating current levels are assumed to be expressed as RMS values unless clearly specified otherwise. RMS values are sometimes referred to as the effective values. RMS voltage is the amount of DC voltage that is required to produce the same amount of power as the AC waveform. The RMS voltage of a sinusoidal waveform is equal to 0.707 times its peak value. The period of a waveform is the time required to complete one full cycle. It is represented by the symbol T and is measured in seconds. One period occupies exactly 360 degrees of a sine waveform. The frequency of a waveform is the number of cycles that are completed each second. It is represented by the letter F and is measured in hertz. The frequency is equal to the inverse of the period and vice versa. In circuits containing only resistors, such as those we have studied thus far, the current and voltage are in phase with each other, which means that they peak at the same moment in time. In circuits containing inductors and capacitors, however, the current and voltage will often not be in phase, and the angular difference between the two waveforms is called the phase angle. On the top portion of this diagram, we see an illustration of when the current represented by the dotted line peaks after or lags the voltage, represented by the solid line. Below that, we see an illustration depicting current leading voltage. Apparent power is the product of the effective voltage and the effective current when the current and voltage are in phase. It is expressed in voltamps rather than watts. The apparent power is positive. The true power is the power in an AC circuit that takes the phase differences into account. True power is the product of the voltage and that portion of the current that is in phase with the voltage. True power is expressed in watts and is always less than the apparent power. During that portion of the cycle where either the voltage or current is negative, then the true power is negative, and at that period of the cycle, the load is forcing power back into the source. The power factor is the ratio of true power to apparent power. True power is the product of the voltage, the current, and the power factor. The power factor is equal to the cosine of the phase angle. In circuits having only resistive components, such as light bulbs, heaters, and composition resistors, the current and voltage are in phase, so the true power equals the apparent power. If you hold a conductor in your left hand so that your thumb points in the direction of electron flow towards the positive terminal, your fingers will encircle the conductor in the direction of the lines of magnetic flux.